We're going to continue our conversation about hypothesis testing by talking about testing a claim about a proportion. So our key concepts, we want to be able to complete a procedure for testing a claim about a population proportion. We're going to do this using the p-value method, the critical value method, and talk about using confidence intervals to do this as well. So these different methods, we're going to be using a normal approximation to a binomial distribution, which we used when we were doing confidence intervals, and we'll continue to use with part 1 of this. And then part 2, we're going to discuss really quick how we might do this in other ways that are more exact instead of an approximation, but they require the use of technology. So our objective is to conduct a formal hypothesis test about a claim about a population proportion. Notation hasn't changed. We have n as our sample size, p as our population proportion, q as 1 minus p, p hat as our sample proportion, where we're taking x divided by n. X is the number of successes that we have in our sample. And our requirements have also not changed. These look familiar from doing our confidence intervals with our population proportions as well. So our sample observations, they need to be a simple random sample. And the conditions for a binomial distribution have to be satisfied. So those were that we had a fixed number of trials, that the trials were independent, and that each trial had categories of success and failure, and the probabilities of success and failure stayed the same in all of the trials. Additionally, we have this idea of the n times p needs to be greater than or equal 5, and also n times q needs to be greater than or equal to 5. So this is the idea that if these things happen, then our sample is large enough that we can use a normal approximation of the binomial distribution. All right. So we'll be using z equals p hat minus p over the square root of p times q divided by n. And when we talk about p-values, these, again, they're automatically provided by technology, but we're not going to be using technology. Instead, we'll be using table A2 to look them up. And then when we talk about critical values, we'll be using table A2 for that as well. We mentioned before, and we want to mention a little bit more in detail here, is that our confidence interval method does not result in the same conclusion necessarily as our p-value method and critical value method. Now, both the p-value method and the critical value method both use the same standard deviation on the claimed proportion of the population proportion. So those two are equivalent and result in the same conclusion. However, the confidence interval method uses an estimated standard deviation based on the sample proportion. And so that one results in a potentially different conclusion. So we have a recommendation that if we're looking to estimate a population proportion, then we should use a confidence interval. But if we want to test a claim about the population proportion, then we should use the p-value method or critical value method. So here we are back to this drone example, where we have 1,009 consumers that are asked if they're comfortable with having drones deliver their purchases. 54%, or 545 of them, respond no. So we want to use these results to test the claim that most consumers are uncomfortable with drone deliveries. So we're going to interpret most to be more than half or greater than 0.5. So first things first, we're going to check our requirements. The first one was that we have a simple random sample. Well, our 1,009 consumers are randomly selected, so we have our simple random sample. Then we need our binomial distribution requirements. So we have a fixed number of trials. There were 1,009. They're independent. One person's answer is not going to impact someone else's. And there's two categories. They're either uncomfortable or they're comfortable with drone deliveries. All right, so we've got our binomial distribution stuff set up. So then we need to check this NP and NQ requirement. Both of these need to be greater than or equal to 5. And if we multiply 0.5 times 1,009, we'll see that they are very much so greater than or equal to 5. So we have all three requirements. We're allowed to use a normal estimation of our binomial distribution to conduct our hypothesis test. So here's a solution with the p-value method using technology. If we use technology, they usually give us a p-value, which means we're going to use the p-value method. So here's a display from a TI-83 or 84 plus calculator, and it shows us a test statistic of z is about 2.55 if we round it, and a p-value of 0.0054 if we round that. All right. So there we have our p-value method with technology. All right. So you'll also notice that it says prop greater than 0.5. So that's saying that our alternative hypothesis that we were testing is that the proportion is greater than 0.5. And these are the results. So hold that thought. We're going to jump over to what if we don't have technology? How can we use table A2 to help us out to get to these same results? And then we'll talk about how we interpret them. So table A2, we don't have technology. Right? So step 1, our original claim is that most consumers are uncomfortable with drone deliveries, and that claim can be expressed in symbolic form as P is greater than 0.5. The opposite of that original claim is that P is less than or equal to 0.5. Right? Even if you're using technology, you should be going through these initial few steps, and I'll say when you'll break off from it. Right? So for step 3, we look at our two things and we say which one of these has the equal sign with it, and our null hypothesis is that one. So our null hypothesis is P is equal to 0.5. Our alternative hypothesis is that original claim that P is greater than 0.5. Now, we should decide on a significance level before you use technology also that we're going to be using. So sometimes your significance level is given to you, other times you need to decide on it. 0.05 is a very common choice, so it's pretty much a safe bet unless you're told otherwise. So at this point, you could jump over and use technology. You know what your significance level is, and you know what your alternative and null hypotheses are, and you've really dove into the problem. If you're using table A2, then we continue on to step 5. So because we're testing a claim about a population proportion, the sample statistic p hat is relevant to the test. So the sampling distribution and sample proportions p hat can be approximated by a normal distribution in this case. We saw that because of our third requirement check working out. We've also seen this previously when we were talking about normal approximations of binomial distributions, and back when we were talking about confidence intervals with proportions. So going into our table. So we find the test statistic z equals 2.55. We can use it, find it by using technology. We can also calculate it. All right, so if we don't have technology available, we use this idea that z equals p hat minus p divided by the square root of p times q divided by n. We know p and q, we know n, and p hat we can find using our sample data that we were given. So 545 divided by 1009 is going to be our p hat value. 0.5 as p was assumed in our null hypothesis, and that's what we use when we're using the p-value method. All right, so we fill all of that in, we do that calculation, we get 2.55 for our z-value, our test statistic. That's the same thing that technology comes up with. So now we go into table A2, and since our alternative hypothesis is that we're interested in being greater than that, we're looking for the area to the right of our test statistic. And if we do that, we look at the value in table A2, it's 0.9946. To find the area to the right, then we're going to take 1 minus 0.9946 and get 0.0054. So our p-value is that. The area to the right under the curve is 0.0054. That's the same p-value that technology gave you. And here's a visual of what's going on there, what the p-value looks like in our normal distribution. So now, regardless of whether we've used technology or table A2, we're back and needing to do step 7 and 8. All right. So step 7. Because the p-value of 0.0054 is less than or equal to the significance level of 0.05, we reject the null hypothesis, right? So if our p-value is less than our significance level, we reject the null hypothesis. And then step 8, we need to interpret this. So because we reject our null hypothesis that the proportion is 0.5, we support the alternative hypothesis of p is greater than 0.5. We conclude that there is sufficient sample evidence to support the claim that more than half of consumers are uncomfortable with drone deliveries. So now I want to invite you to rewind just a little bit. Back at step 6 with the p-value method, just to take you back there real quick, at that point, that's where we were finding our test statistic z. Now, if we're using the critical value method, we're still going to compute that test statistic. So we have our test statistic of 2.55. We'd compute it the same way that we did in our p-value method. And after we know what our test statistic is, then we need to find our critical values. So this is a right-tailed test. So the area of the critical region is the area of 0.05 in the right tail, all right? So we want the value that the area to the right of it is 0.05. So we use table A2, and we go and we find the probability of 0.05 in the body of the table, and we find the z-value that corresponds to that. That z-value is one of those special ones in that little table under the big table. It says z equals 1.645. Now, that z-value that we just found is the boundary of the critical region. So here we have a picture of what's going on here. So we found our test statistic, and then we go and we find our critical value, where the area to the right of that critical value is 0.05, which is our alpha value there. Right? So in our critical value method, we never really take our test statistic to find a probability in the table. Instead, we take the probability, our alpha value that we want, to find a critical value, z. So it's kind of, you go one way in the table or the other way. So you go from a z-value into the probabilities or from a probability out to the z-values. That's the difference between the two methods going on here. So with that critical value now, moving into step 7, what we do is we say, hey, look, the test statistic, it does fall within our critical region. It's to the right of our critical value. So we reject the null hypothesis. All right? And then our conclusion, step 8, comes back together. It's the same idea. So because we reject our null hypothesis, we conclude that there's sufficient sample evidence to support the claim that most or more than half of consumers are uncomfortable with drone deliveries. All right? So it's It's really that step 6 and 7 that are different between the two, and they're both doing basically the same thing using the table. Just the p-value method goes from a test statistic to find a probability, and then compares the probability to our significance level. The critical value method uses our significance level to determine a critical value, and then we compare our test statistic to that critical value to make a conclusion. Same deal, and again, with this proportion thing, they're going to lead to the same conclusion because we're using the same calculation for our test statistic. Now, the confidence interval method. This claim that the majority of consumers are not comfortable with drone deliveries can be tested with a 0.05 significance level by constructing a 90% confidence interval. Now, it's a 90% confidence interval because we want 5% to be to the right, to have this significance level with just 5% in the right tail. And since a confidence interval is both sides and it has both two tails, to have 5% in the right tail, we need to also have 5% in the left tail, combining for 10% in the tails and a 90% confidence interval. So if we construct a 90% confidence interval, we're going to look at our p-hat value. So we have 545 divided by 1009. And we'll go back to what we did in section 7.1 when we were talking about confidence intervals for proportions. And we go through that exact same process that we did there, and we find a confidence interval of 0.514 to 0.566. So the entire range of the values in this confidence interval is greater than 0.5, so we are 90% confident that the limits of 0.514 and 0.566 contain the true value of our population proportion. The sample data appear to support the claim that more than 0.5, more than half of our consumers are uncomfortable with drone deliveries. So notice here we came to the same conclusion. However, if our sample proportion was a little bit closer to 0.5 than it is, it's like 0.54 something, I think, as it is. If it was a little bit closer than that, we might have a different conclusion with our confidence interval method than we have with our p-value and critical value methods. Finding our number of successes. When we're using technology for hypothesis tests of proportions, we must usually have the sample size and the number of successes, but in real applications, the sample proportion is often given instead of X. So a lot of times in real life, somebody will tell you that, hey, 54% of people said no to drone deliveries, right? Instead of telling you 545 of 1009 said no. So the number of successes, we can find that as long as we know the proportion, the sample proportion and the sample size, we can find our number of successes. So this is, again, just remember that algebra is a tool that's useful to you. So for X, N, and P hat, as long as you know 2 out of 3, you can find the third. That's the deal here. All right, so let's take a look at an example of this really quick. So we have a study on sleepwalking, nocturnal wandering, described in Neurology magazine, and it tells us that 29.2% of 19,136 American adults have sleepwalked. So how many people have sleepwalked? Well, we just go through and we say, what is 29.2% of 19,136? Well, that's 5,587.712. And since we don't really want to see what 0.712 of a human looks like, we round it. And so we round it to the nearest whole number, which tells us 5,588 humans, adults, have sleepwalked. All right, so now let's look at testing a claim. So let's say our claim is fewer than 30% of adults have sleepwalked. and we have the information we're given. So let's look at a 0.05 significance level. We're going to test the claim that for the adult population, the proportion of those who have sleepwalked is less than 0.3. So we go through our requirement check. Simple random sample. Yes. All right. Fixed number of independent trials. Yes. All right. And 2 categories. Sleepwalked, not. Good. We got binomial stuff. So we look at NP and NQ. We multiply those with a sample size of 19,136. We are very safe there. So all 3 are met. So step 1, our original claim is expressed in a symbolic form. So P is less than 0.3. That was the claim. So the opposite of the original claim is that P is greater than or equal to 0.3. So which one has the equals? Well, that would be P is greater than or equal to. So we'll make our null hypothesis P is equal to 0.3 using the P is greater than or equal to 0.3 part. So the opposite of that then is P is less than 0.3, and that'll be our alternative hypothesis and also our original claim. So step 4, our significance level was given to us. It's 0.05. And now, step 5, because the claim involves the proportion P and the statistic relevant to this test is the sample proportion, sampling distribution and the sample distributions can be approximated by the normal distribution. Yes. All right. So, if we use technology, we plug all of this stuff in, it tells us Z is negative 0.241, and it gives us a p-value of 0.008. All right, this is what it would look like coming out of StatCrunch. But again, we want to be able to read the technology output, but what we're focusing on is being able to use table A2. We calculate Z the same way that we did before, so we take P hat and we subtract P. That's the P value given to us in our null hypothesis, and we divide it by the square root of P times Q divided by N. In doing so, we find Z is negative 2.41. We agree with that technology output. Now, for this one, we're looking at a left-tailed test because our alternative hypothesis was that P is less than 0.3. So we're looking for the area to the left of Z is 2.41. So for our p-value approach, our p-value method, we're going to look at Z is negative 2.41 in table A2 and find the probability associated with it is 0.0080. So now with our p-value method, since the p-value of 0.0080 is less than or equal to the significance level of 0.05, we reject our null hypothesis. And our interpretation, because we reject the null hypothesis, we support the alternative hypothesis. We therefore conclude that there is sufficient evidence to support the claim that fewer than 30% of adults have sleepwalked. Right. Notice that in this case, our test statistic, so our sample statistic, was really close to 30%. It was less than it, but it was really close to it. But because our sample size was so huge, it still came to this conclusion that, yeah, it's actually less than 30%. So now that we've looked at a couple of examples with the approximating the binomial distribution as a normal distribution situation, let's take a look at a situation where we can't and what we can do when we can't approximate it as normal. So our exact method for testing claims about population proportion, you can do this by hand, but it's honestly a mess. So it's beyond what we're going to do. So what you need to know is things that we need to know to use exact methods are the sample size, the number of successes, the claimed value of the population proportion, and we're going to find a p-value using technology for finding binomial probabilities. Now, these are our binomial probabilities that we're interested in. So if we're looking at a left-tailed test, so our alternative hypothesis has a less than in it, we'll be looking for the probability of X or fewer successes among N trials. If we're looking for a right-tailed test, our alternative hypothesis has a greater than sign in it, then we're looking for the probability of X or more successes among n trials. And if we are looking for a two-tailed test, this is when our alternative hypothesis has a not equal to sign in it. We're looking for twice the smaller of the preceding left and right-tailed values. All right, so our exact method. Let's take a look at an example here. So our gender selection, 10 randomly selected couples are treated with the method. They each have a baby and 9 of the babies are girls. So using a 0.05 significance level to test the claim with this method, the probability of a baby girl is greater than 0.75. So we want to know, is the probability of a baby being a girl greater than 0.75? So let's check our requirements. Normal approximation method, in part 1, that requirement that it needs was step 3, the NP and the NQ being greater than or equal to 5. In this case, NQ is only 2.5, which is not greater than 5. That means that we can't use a normal approximation, right? That means we have to use the exact method. All of the other requirements, we need those things to be true to use the exact method as well. And in this case, we have those things. We have a random trial. We have a binomial trial. So we're good. But that third requirement that we had to use our normal approximation, it fails here. So we'll need to use an exact method. So our null and alternative hypotheses, we find these the same way that we did before. Our null hypothesis needs to have an equal sign in it, and our alternative hypothesis is going to match up with our original claim pretty much always, and it's going to be greater than, less than, or not equal to, depending on what the original claim was. So in this case, the original claim was that P was greater than 0.75. So instead of using our normal distribution, since we can't use our normal distribution, we're going to use technology to find the probabilities in a binomial distribution with P equals 0.75. And because it's a right-tail test, we're looking for the probability of 9 or more successes among 10 trials, assuming that P equals 0.75. Now remember, your binomial distribution table allows you to find these things. But again, it's a pain, and so we're going to stick to, we need technology to do this, and what we're going to be focusing on is reading our technology output. All right, so let's take a look at the stat disk display of what this is. So we're looking for the probability that we're 9 or greater, and there we go. Stat disk, you put in the number of trials, you put in the number or the probability of success, and it gives you this table to work with. So X is 9, and we want 9 or greater, so we look at that right-hand column, and there it is outlined in red. We have a p-value, a probability of 0.2440252. All right. So we look at that and we say, oh, the p-value is high. It's not less than 0.05. And so there's not sufficient evidence to support the claim. We fail to reject the null hypothesis. So there's not sufficient evidence to support the claim that with the gender selection method, the probability of girl is greater than 0.75. Right? This is that double negative thing coming into play, the fail to reject deal. So with our exact method, the actual probability of a type 1 error is less than or equal to alpha, which is our desired probability of a type 1 error. Remember, alpha is our significance level that we're looking at. All right. So we can actually improve the exact method by doing a simple continuity correction. What this does is it improves the conservative behavior of the exact method with an adjustment to our p-value that is obtained by subtracting it from the value that is 1/2 of the binomial probability at the boundary. It's weird, right? So what that looks like. So if we're doing a left-tailed test, what we do is we take the probability that we have X or fewer, which is what we we're going to deal with to begin with for our p-value. And then our correction is to subtract 1/2 of the probability of it being exactly x. All right. For a right tail test, we do the exact same thing. So we have the probability that x or more, and then that was what we had originally. And then we're going to subtract 1/2 the probability that it's exactly x. So we're going to kind of shave that boundary a little bit in doing that. For the two-tail test, this is twice the smaller of the preceding one still, except the little correction thing needs to have happened before we decide which one's smaller, and then double it.